Oh god, here we go. These are the questions. So far, all these questions are baby questions. Just baby problems. This is where we're getting to enemy territory. Okay, we have this slant right here, figure rough inclined plane, blah blah blah. Okay, this is a rough plane. So what am I gonna do? I'm going to show the reaction force exerted on P. And keep in mind, the reaction forces are always, the other name is normal contact force, and normal essentially means the perpendicular force, or just the perpendicular. You know how we do the light ray thing and we draw the normal? That's what normal is, the perpendicular thing. So reaction is always perpendicular. There we go. And then of course the weight. So in these questions, always just label these forces, okay? It's gonna make a difference, I promise. We have mg right here, and it is held in equilibrium, and then the plane is inclined at an angle of alpha. Alpha is less than 45, blah blah blah. String is inclined, blah blah blah. Okay, this is a string. That's interesting. And when the tension in the string is 0.75 mg, so when it's 0.75 mg, P is on the point of moving up the plane. Okay, so we're on the point of moving up the plane, but we're still not moving because the forward force that is 0.75 mg cos alpha, not just 0.75 mg. We're really concerned about this, the component. This is actually just barely balanced by the components or the forces that are acting down the plane. And what are those forces? You have to figure that out, okay? Those forces, among those forces are, one of them is the component of the weight itself. We know if that's alpha, then this is alpha. Oh, by the way, if you're wondering why that's the case, why that's alpha, and I'm sure you've already been taught that, right? If you're not, I don't know what you're doing or what your teacher's doing, but yeah. So like, what I'm gonna do is try to shift to this line over here. We're gonna just bring that over here. So what are we worried of? We're worried about this right here, this alpha. Oh, sorry, let's call it theta. Let's say we don't know that this is alpha yet. Let's say that's just some angle theta that we're interested to find. And so, and this line and this line, these two dotted lines are parallel. Now we need to find out theta. Now we can see that this line right here is just, well, perpendicular to the slope here, so that's 90 degrees, and we know that this is alpha, right? This is alpha, so this is going to be 90 minus alpha, and therefore this, we know that this thing is perpendicular as well, so theta is just going to be 90 minus alpha, so 90 minus alpha, and then you end up with alpha. That's how we know that that's alpha. That's just one of the ways to prove that that is alpha. There are many other ways. Okay, well, let's not waste time. When the tension is this, please, okay, point on moving up the plane. So as I was saying, this force, 0.75 mg cos theta, is like barely enough. Okay, actually not. Like, this force is barely being balanced by the forces in the opposite direction, and the forces there are the components of the weight down the slope. That is mg sine alpha, since the component is opposite to alpha, you're gonna just take sine alpha. I'm sure you know how these components become sine and cos, right? Like, come on, I hope you do. If you don't, I don't know, comment down below. Okay, now this is just one of the forces. Now keep in mind, this is a rough plane. Oh, I just had ice cream today and I feel so terrible. I'm gonna catch a cold. Oof. Okay, let me drink some water. Ooh, needed that hydration. Okay, since it's a rough plane, there's definitely going to be a friction here as well. Okay, that friction is really the deal breaker here, right? If that friction reaches its maximum value and it no longer can increase, okay, it no longer can increase, it has already reached its maximum value, that is when we reach the limiting equilibrium. Actually, no, because the limiting equilibrium is really reached when we're about to move, essentially. Okay, when we're about to move. So like you have 0.75 mg here, sorry, 0.75 mg cos alpha in this direction. This is going to be equal to mg sine alpha plus f max. And it's going to be equal at the limiting equilibrium position. So yeah, there's going to be f max here. Because it just says that it's on the point of moving up the plane, that just implies that you've already reached the maximum force. So that's how you know that you're going to have to use F max instead of just some frictional force. Okay? Now, yeah, what can we do? We can simply... Okay, we just have to find an expression for the magnitude of the frictional force. Oh, so we just need frictional force. So like F max is going to be... what is it? It's just mu r. We know what mu is, don't we? Oh, we don't know mu. Okay, so I guess we can't do that. So we just have to use this information right here. We know it is on the point of moving, but it's not moving. It's still at equilibrium, at rest. So essentially 0.75 mg cos alpha is going to be equal to whatever forces there are opposing that. So we have one of them is mg sine alpha, and the other one is just f max plus f max. And also be sure to write this down, like you're resolving in this direction parallel to the slope. I don't know if they really care about that, but it's just best if you show that. Okay, just maintain, it's just a form of courtesy essentially. Okay, now we're really concerned about f max. In terms of mgna, we have mgna, sorry, alpha. F max is just going to be 0.75 mg cos alpha minus sine alpha. Oh, no, we can't do that, I'm sorry. We can only do this, mg and then 0.75 cos alpha minus sine alpha. That is what we can do. There we go. That's F max. And the coefficient of friction between P and the plane is half. Show that tan alpha is this. So we have been given the coefficient of friction now. And we know that F max is mu r. And if we actually just use this equation here, we might be able to arrive at something, you know what I mean? Preferably tan alpha itself. So F max, mu r, 1/2 r. What is r going to be? Okay, now to find r, we can simply say it's just mg cos alpha, right? No. It is only when you just have a particle just resting here, and not rest, it could be moving, but when no other forces are acting on it. Okay, only just these two, and maybe some forces in the horizontal direction that won't affect the reaction force. Only then reaction is actually equal to mg cos alpha. But now you can see that there is an extra force here, 0.75 mg in this direction at an angle to the slope. That would actually create a vertical component of the particle in this direction right here, just like that. And then r just no longer is equal to mg cos alpha. It's going to be something different. That's what we're going to have to find out. So what we can do is we can resolve this in this direction, like perpendicular to slope. That's how we show that. We can say that r plus 0.75 mg sine alpha is equal to mg cos alpha, and you can see that r is equal to mg cos alpha minus 0.75 sine alpha. This is what we have. Now we know that f max is just mu r. We can actually just use this over here. So half mg, and then we have cos alpha minus 0.75 sine alpha, and that is equal to this thing right here. We're just gonna have to solve this. I'm just lazy. You just don't be lazy when you're solving these problems in the exam. Okay. Now you can see that the mg's just cut off, right? They just cancel out each other. Totally fine. Let's just multiply both sides by 2 so that this 2 just goes away, and then we have a 2 there, so we have like 2.75, and then cos alpha minus sine alpha, this being equal to cos alpha minus 0.75 sine alpha. And you can probably see where this is going. Well, this is just going to be like 1.5 cos alpha. Wait, oh god, I'm at that point where I have to make sure 0.75 times 2 is actually 1.5 cos alpha. Okay, oh god, it's totally fine actually. Just be sure to double check everything. Like in the exam, I doubt myself a lot. I just check one thing over and over again. It's a bad habit, but an excess would be a bad habit. But like being a little bit concerned, it is fine. Okay. Okay, we have cos alpha minus 0.75 sine alpha here. Look at that handwriting. So we're just going to bring the cos alphas to one side. So we're going to have 0.5 cos alpha here, and on the other side we're going to have 2 minus 0.75. I think that's 1.25 sine alpha. Okay, now we can divide both sides by cos alpha, or essentially just bring this to this side, so you get tan alpha, and then bring the 1.25 down to this side, so you have 0.5 divided by 1.25. 0.5 divided by 1.25 is actually just 2 by 5, and voila, we have our answer. And also, let's just write down shown. Okay, the string breaks. Oh wow. Determine whether P remains at rest. You must justify your reasoning. Alrighty, that's really interesting. So now there is no longer P. Sorry, what? Not P. A string, and therefore no longer. Wait, no. Okay, never mind. Okay, let's just draw this again. Okay. There we go. And there's P. We have mg. We have alpha. We know tan alpha is 2/5. God. And we have reaction. I don't think. Do we need that? No. Let's just keep that. Okay, that's fine. Okay, let's just write this down as like mg cos alpha. Okay. Now, no more strings attached. No more strings attached here, and well, what other forces are there? There's gonna be friction. Why? Because naturally this particle is gonna try to move down, because, well, there's a component of weight acting down the slope in this direction. So of course naturally it's gonna try to move down because there's a resultant force, and I'm saying this like resultant force. Okay, because in reality there may not be a resultant force if the forces are balanced. How can it be balanced? Well, remember how the surface is rough. That roughness can give this friction, give this particle some friction, right? And that friction is just going to be in the opposite direction, trying to oppose the component of mg here, which is mg sine alpha. So essentially this object will remain at rest if this mg sine alpha is equal to the frictional force, not the F max. It could be equal to F max. In that case it would be on the point of moving down, but it could just be below the below the maximum friction, and still, you know, just be at rest. What can we do, right? But the P remains at rest. What we can do is find out the maximum friction. Okay, let's find the maximum friction first. Maximum friction is going to be equal to, okay, we know the coefficient of friction, which is half times the reaction force. Reaction force is just mg cos alpha. What is cos alpha? Right, what is cos alpha? How do we find that? Now you may be tempted to maybe find out alpha first by doing tan inverse 2/5 and get some value that you're going to round off, and then use that same angle inside cos alpha. But that's just not going to give you the best answer, not the most accurate answer. So what instead you can do is this: form a triangle. That is alpha. Let's say it's a right angle triangle, and this is what we're going to try to do. What is tan? Tan is opposite divided by adjacent, so this is 2, this is 5. And if we just find out the hypotenuse here, hypotenuse is going to be 2 squared, that's 4, plus 5 squared, that's 25, so it's just root 29. Now, essentially, you can find out an expression, or find out expressions for sine alpha and cos alpha. You need sine alpha as well, as you can see. So half mg times what cos alpha, that's what we're doing. So cos alpha is adjacent by hypotenuse, that's 5 divided by root 29. There we go, 5 divided by root 29, and this is 5 mg divided by 2 root 29. There we go. And that is F max. We just found that out. Now what we want to do is find out the force that is acting downwards. Force acting downwards. Force acting downwards. Acting down the slope, actually. Downwards could just imply that vertically downwards, but so it's best if we just write down the slope. The force acting down the slope is equal to mg sine alpha, so mg times sine alpha. Sine alpha is opposite, that's 2 divided by the hypotenuse. Okay, now you have to compare F max in this. Okay, we can see that this is just 2 mg by root 29, and this is 2.5 mg by root 29. So F max is actually greater than 2 mg divided by root 29. Therefore, what the fridge? Okay, therefore this force, the component of weight, which is 2 mg by root 29, is balanced by the available friction. Or you could say something like friction is high enough, the max friction is high enough that the component of the weight is balanced before reaching the max friction. Okay, no, what am I saying? You could just say that this is balanced by the available friction. That's fine. Available friction, and in the brackets, I guess you could just say what the friction is. The friction is just going to be equal to this, right? It's going to have to be equal. There we go. And that's just it. And therefore, you can say that determine whether P remains at rest. Oh, you have to mention that. Therefore, P remains at rest. P remains at rest. Do mention that. There we go. All right. Next question.